Welcome to the engineering video series. This tutorial describes how to upgrade a VADOSEW file created in GeoStudio 2012 or 2016 to the latest version, GeoStudio 2018. In GeoStudio 2018, the multiphysics analysis functionality for the heat and mass transfer products removed the need for VADOSEW as a standalone product, because VADOSEW analyses were essentially coupled water and heat transfer analyses. The physical processes unique to VADOSEW are now available in SEEPW, CTRAN-W, and TEMP-W. A SEEPW analysis may now include either isothermal or thermal vapor transfer, with the latter requiring TEMP-W. GeoStudio 2018 has improved boundary conditions for simulating atmospheric coupling. The land-climate interaction boundary condition in SEEPW simulates evapotranspiration based on climate and vegetation conditions. The surface energy balance boundary condition in TEMP-W computes ground heat flux for varying ground cover conditions, including snowpack and vegetation. A VADOSEW analysis created in GeoStudio 2012 or 2016 automatically changes to a SEEPW analysis when opened in GeoStudio 2018. A climate boundary condition defined in VADOSEW becomes a land-climate interaction boundary condition. The original climate data table upgrades to a new data set where each parameter is a function of time. A project start date is required to define the estimated solar radiation function and minimum-maximum relative humidity and temperature functions. By selecting these parameter functions from the drop-down menus, the land-climate interaction boundary is complete. Another change associated with upgrading to GeoStudio 2018 is the removal of automatic time stepping. Finally, surface layers are not required to apply the land-climate interaction or surface energy balance boundary conditions. Let us consider a VADOSEW file in GeoStudio 2016. In the Key In Analyses window, we can see that this VADOSEW analysis includes oxygen transport in addition to water and heat transfer. The material properties defined for the VADOSEW analysis are the hydraulic, thermal, and gas properties. The hydraulic properties are the same as those specified in a SEEPW analysis and include the volumetric water content and hydraulic conductivity functions. Similarly, the thermal properties are defined with either the full or simple thermal material models, which are also available in TEMP-W. Lastly, the gas properties include some basic inputs for radon or oxygen transport within the model domain. The primary boundary condition of interest in a VADOSEW analysis is the climate boundary condition. This boundary condition requires information on climatic conditions, including air temperature, relative humidity, wind speed, and precipitation, which were entered into the climate data table, and inputs to calculate net radiation and potential evapotranspiration. Finally, the influence of root water uptake is also considered given the specification of vegetation functions. The climate boundary condition, represented by the green arrows, is applied to the surface layers along the top of the modeled geometry. Now let us open the file in GeoStudio 2018 by right-clicking on the file, selecting Open With, and choosing GeoStudio 2018. A pop-up dialog indicates that the file automatically upgrades to GeoStudio 2018 upon opening and provides the option to view the upgrade details. When clicking on Details, a web browser opens with a detailed list of the potential changes when upgrading the file. In this case, the list indicates that VADOSEW is no longer a separate product and that the file is converted to a SEEPW analysis with a land-climate interaction boundary condition. The knowledge base article referenced here provides a more detailed description on upgrading VADOSEW files to the new GeoStudio 2018 format. After reviewing the upgrade details, let us go back to GeoStudio 2018 and view the upgraded file. In the Define Analyses window, the Physics tab indicates the physical processes included in the analysis. In this case, only the default process associated with SEEPW, water transfer via pressure and gravity gradients, is selected. To replicate the physical processes associated with the original VADOSEW file in this SEEPW analysis, we can add isothermal and thermal vapor transfer, heat transfer, and gas transfer. These additional physics require temp W and Ctran W. Under the Time tab, we can see that the adaptive time stepping option is no longer available. Consequently, smaller time step increments should be defined for analyses considering climate effects on the ground surface. Time increments between 2 and 6 hours are recommended. Let us now review the upgraded material properties in the Define Materials window. Under the Thermal tab, the thermal properties from the original VADOSEW analysis now define the simplified thermal material model. Under the Hydraulic tab, the material parameters associated with the hydraulic properties of the VADOSEW 2016 analysis were imported into a saturated-unsaturated material model. Finally, under the Gas tab, we must specify the gas transport and storage properties as different inputs are required in GeoStudio 2018. We can see that the materials appear on the domain as they were in the original VADOSEW file. After considering the analysis definition and material properties, we will review the updated boundary conditions. The data table used to define the VADOSEW climate boundary condition was imported into GeoStudio 2018 as a data set. In the Define Datasets window, we can view the corresponding dataset. The listed parameters define climate functions, which are available in the Define Climate Functions window. Each climate function's name corresponds to the original climate boundary condition name and the involved parameter. The function type depends on the parameter. For example, the maximum and minimum air temperatures are imported into the function type Daily Min-Max Sinusoidal Distribution, where the minimum air temperature corresponds to 1 a.m. and the maximum air temperature occurs at 1 p.m. The maximum and minimum relative humidity values also create a daily min-max sinusoidal distribution function. Precipitation and wind speed are imported as step data point functions. The climate functions automatically define the new land climate interaction boundary condition with the same name as the original VADOSEW climate boundary condition. If the VADOSEW climate data table did not include user-defined potential evapotranspiration, the Penman-Wilson method is automatically selected for the evapotranspiration method in the new boundary condition. This is similar to the method used in VADOSEW 2016 and earlier versions. If user-defined potential evapotranspiration data was included in the VADOSEW climate table, then a potential evapotranspiration function is imported with the climate dataset and the user-defined evapotranspiration method is selected in the land climate interaction boundary condition. When the energy data source for the original climate boundary condition was user-defined net radiation, the land climate interaction boundary condition uses the net radiation option. The inputted net radiation data is imported with the climate dataset and the corresponding function is selected. If the original boundary condition estimated the net radiation, the solar radiation option is selected in the land climate interaction boundary condition. The latitude and project start date imported from the VADOSEW analysis generate the estimated solar radiation function. This function can either distribute radiation sinusoidally or provide a constant average radiation value for each day. The solar radiation option requires an albedo function, which is defined by clicking on the ellipses button and adding a new function in the Define Climate Functions window. VADOSEW automatically calculated snow depth during solve time. In GeoStudio 2018, the land climate interaction boundary condition provides the option to estimate snow depth based on the climate data and specified inputs, or import a snow depth function if the data is available. Upon upgrading a VADOSEW file, the snow definition is set to the calculated option and the corresponding function is available by clicking on View Function. If the VADOSEW file included vegetation functions, they are also imported with the climate dataset and the Use Vegetations Functions toggle is active under the Vegetation Data tab. Two new functions are necessary for defining the vegetation parameters in the land climate interaction boundary condition: the normalized root density and the soil cover fraction functions. To create these functions, click on the ellipses for each parameter to open the Define Climate Functions window. When simulating root water uptake on the domain, the Penman-Monteith method is the recommended approach for determining evapotranspiration. Vegetation effects may also be considered in the surface energy balance boundary condition by defining a vegetation height function. The last option available in the land-climate interaction boundary condition is the definition of the minimum pore water pressure at the associated nodes. The default selection when upgrading from VADOSEW is the calculated option. To define this relationship manually, choose the user-defined toggle, click on the ellipses button, and create a new function in the Define Climate Functions window. With this option selected, the solver considers the inputted minimum pore water pressure at the corresponding time step to ensure that the evaporative flux does not cause the pore water pressure to drop below the specified value. If the pore water pressure does drop below this minimum value, the time step is resolved with the pore water pressure value applied as the boundary condition. The hydraulic boundary conditions are defined on the domain as in the original VADOSEW file. The thermal boundary conditions for the original VADOSEW model also appear on the domain because we added heat transfer to the physical processes included in the analysis. However, because the climate boundary condition upgraded to the land climate interaction boundary condition, which considers only evapotranspiration flux, there is no thermal boundary condition at the ground surface. Thus, for an analysis including heat transfer, a thermal boundary condition should be created and defined to represent the surface conditions. Similarly, the gas boundary conditions were not upgraded and must be redefined. Finally, surface regions present in the original VADOSEW analysis are imported into GeoStudio 2018 to ensure that the geometry and material information is consistent in the updated file. Although surface layers are no longer necessary for applying the land-climate interaction or surface energy balance boundary conditions, they do provide a convenient approach for creating cover layers. In summary, VADOSEW files upgrade to CEPW analyses when opening in GeoStudio 2018. Water transfer is the only default physical process selected upon upgrade, thus additional processes must be specified in the Define Analyses window. The original materials are imported into the new file with the hydraulic and thermal properties automatically populated. The climate boundary condition upgrades to a land climate interaction boundary condition, with the climate data table imported as a data set and the corresponding parameter functions generated automatically. To finish defining the land climate interaction boundary condition, an albedo function must be defined, in addition to normalized root density and soil cover fraction functions if root water uptake is considered. Heat transfer analyses require a new boundary condition simulating ground heat flux at the surface, as the land climate interaction boundary condition only considers water transfer. For further information on the new land climate interaction boundary condition or the improvements made to GeoStudio 2018, please refer to other tutorial videos or the Heat and Mass Transfer Engineering book. Thank you for watching.